So welcome everybody to today's IAMP seminar. As you know, this is a bi-weekly event of the International Association of Mathematical Physics. And we are very happy to have Niels Benedikter today, who will speak about bosonization of large systems of interacting fermions. So please go ahead, Niels.
Thank you very much for the invitation. So I hope there's not too much overlap of the audience with last week in Toulouse at the workshop, because I will be giving very much the same talk. All right, yes, I want to talk about some recent work about large systems of interacting fermions at high density and bosonization methods allowing us to compute post-Hartree-Fock effects in such systems. Okay, so this we can think of that as a very simple model of electrons in a metal, maybe the most simple quantum mechanical model we can have for electrons in a metal. So we just take n spinless fermions on the torus of side length 2 pi. Side length is fixed for us, and that means the wave function of the system is an element of L2 of the torus T3 to the n. Alternatively, think of it as the n-fold tensor product of L2 T3. Now, these are fermionic particles, so of course the wave function should be totally antisymmetric. So if I have a permutation of the n arguments here, I should be picking up a sign of the permutation. And the Hamilton operator is the one very much standard in condensed matter theory. We have a Laplacian, a sum of Laplacians describing the kinetic energy of electrons. And then we have the interaction term, which describes the repulsion between electrons. In this model, there are only electrons. There are no nuclei. There's no periodic structure of the material. So it's really just electrons moving in a box. The interaction potential could be the Coulomb repulsion, if you think really about the fundamental electrons, if one thinks of this more as an effective model for fermionic quasi-particles, this may be a screened interaction here. So it's of course easier to work with potentials that are less singular than the Coulomb repulsion, but they also have a physical motivation. Now, the system, of course, very difficult to analyze since the number of particles is just gigantic, something of order n particle number n of the order 10 to the 23, and therefore we're interested in effective theories for large particle number. Okay, so let me describe a little bit more precisely what I intend by high density systems. So we really want to study some kind of system that we can think of as having a behavior in some sense close to mean field behavior. So yes, we take the particle number n to infinity. So having a fixed size system, that means also the density proportional to n tending to infinity. We want the interaction potential to be weak, so that each individual collision between electrons or fermions has a small effect. But since we are at very high density, we have a distance between particles that is typically much shorter than the range of the interaction. So each of the particles is going to see a very large number of other particles, and we want to balance these effects such that weak interaction for individual collisions, but many collisions, comes out to the same order of magnitude as the kinetic energy of the system. Okay, so how exactly do we have to balance the parameters in the model? Well, to get a first impression, we can just look at the simplest possible fermionic state coming to our mind, which would be an antisymmetric tensor product or a Slater determinant, right? So my wave function psi would be a wedge product of n orbitals, each of these living in L2 over the torus, or written more explicitly, psi of x1 to xn would be this determinant of phi I xj. Now, if I look at non-interacting fermions as a very first approximation, then the ground state is, of course, a Slater determinant of the eigenfunctions of the Laplacian. My Hamiltonian is just the sum of Laplacians in that case. So that means the eigenfunctions are plane waves. My normalization on the torus of side lengths 2 pi, they would be phi j of x, 2 pi to the minus 3/2 e to the I k j x, where the momenta k, j are in the lattice of momenta set to the 3. Okay. Now, not having any interaction in the system, of course, these are going to occupy the states with the lowest possible kinetic energy. So minimizing the Laplacian and Fourier representation is k squared. So I should just start by putting in one particle at the origin, then I occupy the states close to the origin, and I go outward in shells, occupying higher and higher momenta until I have all the n particles in my system. All right, so I'm going to fill up a ball in momentum space. That's called the Fermi ball. Right, the Fermi ball I denoted by BF. That's really just all the possible momenta in the momentum lattice up to the Fermi momentum, which is this 3/4 pi to the 1/3 n to the 1/3. Right, I can just determine that very simply by saying, okay, I take the volume of the ball in the continuum. I think of every lattice point as having a little cube of side length 1 attached to it, and I count the number of cubes inside the system, right? So that immediately gives me that the Fermi momentum should be radius proportional to number of particles to the 1/3. Okay, so the result for the kinetic energy is, well, I should just take sum over k squared for all the occupied momenta. So I'm doing the sum over all k in the Fermi ball of the function k squared. And that, of course, gives me n to the 5/3, right? That's n momenta, where most of the momenta being close to the Fermi surface are of order n to the 1/3. Gives me an n to the 5/3. On the other side, if I now put back the interaction energy in the model, so I take a non-vanishing potential, but I evaluate it in the same trial state, the density of that system is constant in the box. Right? The plane waves have the same density everywhere. So the potential energy is just going to be of order n squared, or number of possible pairs in the system. Okay, so this n to the 5/3 from the kinetic energy should be balanced with n squared from the potential energy. So if I put a coupling constant of order n to the minus 1/3 in front of the interaction, I balance potential and kinetic energy, at least in this trial state. Okay, now I want to make one more observation on the physical scales in the problem, which is the Fermi momentum, right? That's what we just had on the last slide. Here in the Fermi ball, Fermi momentum is of order n to the 1/3. So that means also the typical velocity of a particle is going to be of order n to the 1/3. Well, that means it's actually fairly reasonable to rescale time so that we consider typical times of order n to the minus 1/3. We could consider longer times. That's, of course, more difficult. We shouldn't consider shorter times than n to the minus 2/3, n to the minus 1/3. N to the minus 1/3 is exactly the time in which a particle may cross the entirety of the box, in which it experiences many collisions with other particles, so that my mean field setting makes sense. Okay. So we should not go shorter than n to the minus 1/3. So we do go to times of order n to the minus 1/3, which means after rescaling the time in front of the time derivative in the Schrödinger equation, we get an n to the plus 1/3. Okay, in front of the interaction, I have the n to the minus 1/3 from the choice of the coupling constant. And now I just do a trivial trick. I define an effective Planck constant, h bar is n to the minus 1/3. And I multiply both sides of the equation by h bar squared. Okay, so in front of the time derivative, an n to the 1/3 cancels an h bar, and I will be left with an remaining h bar, exactly where it should be in the Schrödinger equation. In the Hamiltonian, I will have an h bar squared in front of the Laplacian, as it should be in the Schrödinger equation, and my coupling constant becomes 1 over n now. So that looks very familiar to everyone working with mean field limits. You have a 1 over n in front of the interaction, but it's here coupled also to a semi-classical limit h bar to 0. Of course, h bar for the whole entirety of my talk will always be n to the minus 1/3. Now, we could write everything in terms of n, but I prefer thinking of h bar as a semi-classical parameter. I think it clarifies the ideas. Okay, so this is the Schrödinger equation I'm going to study for the rest of this talk. I will look at its static properties, ground state energies, excitation spectrum. I will also look at its dynamics, and I will look at the properties of its ground states. Okay, so the simplest approximation we can do for a fermionic system after density functional theory is Hartree-Fock theory. So that means, for example, for the energy, right, the energy would usually be obtained by minimizing expectation value of the Hamiltonian over all the Hilbert space. But in Hartree-Fock theory, I want to do that only over Slater determinants, or anti-symmetrized tensor products. So my only degrees of freedom in this variational problem that remain will be the choices of the orbitals phi. Phi can be optimized over all possible choices in L2, T3. But what I'm not permitting are linear combinations of Slater determinants. Okay, now already this is quite an involved problem, so it's not at all easy to find the solutions of the Hartree-Fock variational problem. And in general, plane waves are not global or local minimizers. One thing we can say is that in our setting, on the torus translation invariant with periodic boundary conditions, plane waves are a stationary point. Okay, so in fact, we have recent results from 2019. Gontier, Heinzel, Levin showed a lower bound, and Gontier, Levin showed an upper bound on the Hartree-Fock ground state energy. So they were looking at the thermodynamic limit with Coulomb interactions and with spin in the system. And they showed that in this setting, actually, the Hartree-Fock ground state is not plane waves. It is significantly lower than plane waves, but not too much lower. I mean, it's actually lower by a pretty small amount, by something like e to the minus density to the 1 over 6. But it is for sure lower than the energy of plane waves. Now, we have, however, exceptional cases like our setting, where we are on the finite torus without spin. We take the potential to be with positive Fourier transform, and we assume that the particle number is such that it exactly fills up a ball in momentum space. Under these somewhat exceptional assumptions, we can show that, yes, the Hartree-Fock minimizer is actually given by plane waves, and the ground state energy of the Hartree-Fock variational problem is the energy of just plugging in the plane waves. Okay, but that is highly non-trivial and in general not true. So what can we really say about validity of Hartree-Fock theory? Well, one thing that we have trivially is Hartree-Fock theory yields an upper bound, right? That's really obvious since the true ground state energy En is just the infimum over all expectation values, while Hartree-Fock energy is the infimum over a smaller set, namely only expectation values of Slater determinants. Okay. So in general, Hartree-Fock theory is only an upper bound. In some scaling limits, for example, at high density, or in our case, in this mean field semi-classical scaling, it was shown by Graf and Solovey in 1994 that Hartree-Fock theory becomes optimal at a large particle number So in fact, the true ground state energy becomes equal to the Hartree-Fock energy plus a small o of 1 as n goes to infinity. Okay, where this Hartree-Fock term here has two contributions to it. It has a Thomas Fermi term, which is kinetic and direct term, and it has the exchange or Dirac term, which is going to be of order 1. Right. So we have the Hartree-Fock energy order n and order 1, and an error of order small o of 1. Okay. And in this case, yes?
On your previous slide, where's the difference coming from the finite box result to NUMS result? Is it the Coulomb interaction, or can you pin it down?
So we believe that with Coulomb we believe that in the finite volume without spin and with Coulomb interaction, at least for a small coupling constant, still the plane wave state is the minimizer. So it's different effects. Either you permit a large box or you put a large coupling constant to make this plane wave state break down as the Hartree-Fock minimizer.
Okay, thanks.
Okay, so according to the result of Graf and Soloway and the one I mentioned before on this slide, we know that in our scaling limit, the true ground state energy is given to relatively high accuracy by the energy of plane waves. And we can ask, what are really the limitations of Hartree-Fock theory then? Well, one possible limitation is this one here. Namely, you may look at different universality classes or phases of the fermion gas. We have two important universality conjectures. One goes back to Landau from 1956, who said that a Fermi gas in 2 or more dimensions should, under very general assumptions, behave as a Fermi liquid, as long as there is no superconductivity at least. So that means primarily that it should behave almost as a gas of non-interacting fermionic quasiparticles. On the other hand, Haldane in 1981 claimed Luttinger liquid universality. So that states that in 1 dimension, the behavior of a gas under very general assumptions should always be very similar to Lieb and Mattis' 1965 exact solution of the Luttinger model, which is a specific model of fermions in 1 dimension with 2 species of fermions that have each a linear dispersion relation. Okay, so that's fairly generic. So what can you think of to distinguish these 2 universality classes? Well, the prime signature would be to look at the number of fermions with a specific momentum k in the ground state. Right. In the non-interacting case, here in the graph on the left, you would have an occupation number equal to 1 inside the entire ball until you reach the Fermi momentum, and then the occupation drops to 0. Now, the thing is, in Hartree-Fock theory, you get exactly the same thing, because we show that at least in the mean field limit, the Hartree-Fock ground state is actually the plane wave state, which corresponds to the filled ball. So in our mean field setting, Hartree-Fock theory produces a state that cannot be distinguished from the non-interacting setting. On the other hand, Landau tells us that the system should behave like a Fermi liquid. The Fermi liquid would be characterized by number of fermions with momentum k, while being very close to 1, then dropping down a little bit before reaching the Fermi momentum, jumping almost to 0, and then tending very quickly to 0. On the other hand, the Luttinger liquid would be characterized by having a continuous occupation profile. So if you reach the Fermi momentum, there's only 1 single point of infinite derivative, but the profile is continuous. Okay, and clearly Hartree-Fock theory doesn't permit us to distinguish these two cases. So if we are asking, can we say anything about these two universality classes? Certainly with Hartree-Fock theory in the mean field limit, we cannot. Hartree-Fock does always gives us the constant occupation number 1 inside the Fermi ball and constant 0 outside. Okay, so what has been done? Well, this has actually been studied quite a lot. Let me just mention some of the most important results. So the d=1 case has been treated by Benedikter, Galavotti, and Mastro Pietro in 1992 by a renormalization group analysis, and they were actually able to show that the system is a Lartinger liquid. I think the Fermi liquid has attracted also a lot of attention, so I'm not going through the complete overview of what has been done. But I think the most well-known results are the ones of Feldman, Knörrer, and Trubowitz that wrote a long series of 12 papers where they showed that in 2 dimensions with an asymmetric Fermi surface, you do have a Fermi liquid. The asymmetric Fermi surface for them serves to suppress the effect of superconductivity. Turns out in the mean field case, it seems that actually superconductivity is generally suppressed to be an extremely tiny effect that we cannot see. So we do not need to make these assumptions like asymmetric Fermi surface. Okay, so how can we go beyond Hartree-Fock theory? So for us, the most natural quantity to look at is we look at the ground state energy of the many-body system. So the result that we were able to achieve relatively recently in the mean field limit is that if the potential is non-negative and satisfies some integrability condition of its Fourier transform, then the ground state energy is given by the 2 terms that are already contained in Hartree-Fock theory, but we obtain 1 term more that in physics literature would be called the correlation energy, which in our scaling is of order n to the minus 1/3, up to an error that is much smaller than that. And the energy of this correlation energy can be obtained by something called the random phase approximation that in the physics literature, and that tells you that this constant here should actually be given by this long integral written here on the last line. Okay, and the proof of this result goes through a rigorous approximate bosonization method, which I want to explain in the following. Okay, so historically, where does this come from? Goes back, I think, until Wigner in 34 and Heisenberg in 47, who looked at standard quantum mechanical perturbation theory with the Coulomb potential. That was the prime interest. And they noticed that there's severe divergence of the perturbative result already at 2nd order. Then, short time afterward, Marke noticed that there can be done a partial resummation of the most divergent terms in the perturbation series that formally sums up to a logarithm, even though outside its radius of convergence. But if you just formally make this replacement of the series, you notice that it cures the divergence. Okay, then Bowman-Pines in 53 gave another approach to the problem, and they noticed that it's related to the emergence of some form of collective excitations in the system, which are called plasmons. They computed explicitly the energy of the plasmon oscillations, and they find a dispersion relation for the plasmons that can actually be experimentally verified. So I think this had a big impact in theoretical physics. Then Zawada, Bruckner, Fukuda, and Brout shortly after gave an explanation of the results of Marke and Bowman-Pines in terms of a formal bosonization of pair excitations, particle-hole pair excitations over the Fermi wall. And I think this is really where this bosonization idea emerges clearly for the first time, and which very much motivated our approach. And then Gell-Mann and Bruckner also in 1957, they went back to approach more similar to the one of Macke. They analyzed systematically the perturbation series, and they noticed that it can really be resummed in a systematic way that permits you to obtain finite corrections to Hartree-Fock theory. Okay, then in the mathematical community, we came back to this problem in 2020, so we were able to find a rigorous way of formulating bosonization that's permitted us to get an upper bound on the correlation energy, an optimal upper bound equal to the formula I showed on the previous slide. And then shortly after that, we also proved the corresponding lower bound. First for small potential, and then there was work by Christiansen, Heinzel, and Nahm, and by myself, Marcello Porta, Benjamin Schlein, and Robert Seiringer, where we established the lower bound also for more general potential. And then recently, this has been also extended by Christiansen, Heinzel, and Nahm with a slightly different bosonization method to include the Coulomb potential. Excuse me, should I look at the questions, or does someone monitor questions?
You don't have to look at the chat.
Okay, thanks. Okay, so let me explain the key ideas of this bosonization method before eventually coming back also to the Fermi liquid problem. So we always work in second quantization. So we put the whole theory on Fock space. Fock space that is just a direct sum of the Hilbert spaces with different particle number, right? So the system with small n particles would be described on the antisymmetric L2 over the torus T3n. We do the direct sum of that. So the elements of the direct sum are really sequences where psi0 is a 0 particle wave function, psi1 is a 1 particle wave function, psi2 is a 2 particle wave function, and so on. And then we generalize the Hamiltonian to that space. Of course, that should act in every sector for every fixed particle number as the original Hamiltonian. Now, the convenient thing in Fock space is that you can give a representation also different from the original one on each sector, namely by introducing creation and annihilation operators. So the annihilation operator, so creation operator A star K, that creates a plane wave of momentum K in the system, does the following. It takes the n particle wave function psi n, it tensors to that an additional plane wave with momentum K, then it antisymmetrizes to stay inside the fermionic space, and it normalizes by a conventional factor. Instead, the annihilation operator acting on psi n removes one variable from the wave function by integrating it out against the plane wave. Let's do like a partial scalar product in the first variable with the plane wave. And I put the conventional normalization. So in terms of these creation and annihilation operators, the Hamiltonian has this form here on Fock space written in blue, which is the kinetic energy is represented by h bar squared, dispersion relation p squared, and then an annihilation operator AP, followed by a creation operator A star P. The interaction becomes a quartic expression, and that's a general rule in second quantization. A non-interacting system is represented on Fock space by a quadratic Hamiltonian. The interaction, the pair interaction, is represented by a quartic Hamiltonian. And this Hamiltonian really restricted to the n particle sector agrees with the Hamiltonian I wrote down in the beginning. The advantage of this representation is that the creation and annihilation operators satisfy very simple anti-commutation relations. It's the canonical anti-commutation relations, CAR, which tell us that an A star with any other A star anti-commutes, while an A annihilation operator with an A star creation operator anti-commutes up to a Kronecker delta PQ. Okay, so in practice, just knowing these relations permits you pretty much to do all possible computations with the system. The only other ingredient you need is the zero particle state, that is also called a vacuum vector and denoted omega, which is the sequence that has 1 in the zero particle Hilbert space and then 0, 0, 0 in all the other sectors. Okay, so going back to Hartree-Fock theory, we can now write the Hartree-Fock minimizer in second quantization. The first quantization, that used to be a Slater determinant of plane waves, so wedge product of FKs with momenta k in the Fermi ball. In second quantization, we represent that by A star k creation operators applied to the zero particle state. So we start from the vacuum and we add plane waves until we've built again the same Slater determinant. Okay, and remember the Fermi ball, this was this ball in momentum space on the momentum lattice of momenta up to constant times n to the 1/3. Okay, now our goal is to manipulate our Hamiltonian in this second quantization framework into an expression that is explicitly quadratic in some well-behaved operators, because quadratic Hamiltonians are effectively non-interacting and can always be understood through Bogoliubov transformations, to which I will come back later. Okay, so recall the starting point for us is now this fermionic Hamiltonian. Non-interacting part quadratic in creation and annihilation operators plus interaction quartic. Okay, so at this point, I want to apply a first unitary transformation to this Hamiltonian, which is a particle-hole transformation that serves essentially to isolate the effect of the Hartree-Fock minimizer from the Hamiltonian and leave us in a description that considers only the excitations over the Hartree-Fock minimizer. Okay, so the particle-hole transformation is defined as a unitary on Fock space. And to define a unitary on Fock space, it is sufficient to say what does it do to the zero particle, the vacuum state, and what does it do to creation operators. So the vacuum state under the particle-hole transformation maps on psi f, that's the Fermi ball state, the wedge product from the previous slide. Instead, the creation operators map as follows. And A star k, creation of a particle with momentum k, after particle-hole transformation is still a creation of a particle, A star k. Non-trivial thing is, if the state had already been occupied in the Fermi ball, then I want to transform A star k into an AK. So in the new representation, the creation operator actually corresponds to making a hole inside the Fermi ball. So this hole really behaves exactly like a fermionic particle then again. Okay, so we can apply this transformation to the Hamiltonian. So conjugate the Hamiltonian with RR star. You get a lot of terms, of course. For example, from the interaction, you have 4 operators. For each of them, you have to distinguish inside or outside the Fermi ball. Does it become creation or annihilation? You get 16 possible combinations. When you do that, they go inside this last term here, Q-like quartic. In the beginning, that term is not going to be normal ordered. So you will have different orders of A star and A operators. We want to have them all ordered with the A stars on the left and the A's on the right. But when you reorder them, you pick up anti-commutators, which are Kronecker deltas. So that reduces the number of operators in that term from quartic to quadratic or even to 0 operators. And if you work that out carefully, you'll find that everything that contains 0 operators after normal ordering is, of course, a constant, and that constant is exactly the Hartree-Fock energy. It has to be like that, right? Because what remains is normal ordered. So in the new representation acting on the state with 0 excitations, the Q term here is going to vanish. So in the new representation, this is the only term that will be left. And of course, that has to be the Hartree-Fock energy. I think the kinetic energy is also an interesting example where you see the effect of this particle-hole transformation, and that the particles outside the Fermi ball, while they keep the energy, just p squared. So energy of a mode outside the Fermi ball will be described by h bar squared p squared a star p a p as before. But a mode inside the Fermi ball corresponds to making a hole, so it has an energy of minus h squared. Okay, so this term that counts particles outside the Fermi ball with a p squared and holes inside the Fermi ball with a minus h bar squared, I summarize it and call it h kinetic. Okay. Now, the one important observation you make about this transformation result is that you can define certain, we call them collective pair creation operators, by the formula indicated here. So this would be creation of a particle outside the Fermi ball, creation of a hole inside the Fermi ball, with momenta restricted to have difference k, but then summing of all possible ways of creating such an excitation. This operator we call b star k, and with this definition, you observe that the transformed interaction takes a very nice form, namely the term q here at the end, the quartic one, becomes a 1 over n sum of k, v hat of k, and then I get this quadratic expression in terms of the newly defined b operators. So I get this 2b star k bk, and I get the b star and the bb, to recognize has exactly the form of a Bogoliubov Hamiltonian, for example, in the theory of Bose-Einstein condensation. There are some additional terms to that. We call them the non-Bosonizable terms because they cannot be expressed in terms of these pair operators b star and b, but they can generally be estimated, and I will forget them for the purpose of this talk. Of course, you have to control them rigorously then, which is not so easy, but it doesn't affect the key ideas of the approximation. So observation number 1 is the Hamiltonian becomes quadratic in the new operators. Important observation number 2 is that these b star and b operators have nice commutator relations, namely approximately bosonic, which means a b star with a b star commutes. That's exactly as it would be for bosonic particles. A b with a b star, well, if it was bosonic up to a normalization constant, you would have a Kronecker delta KL. Now we have a delta KL plus an error term, which is an operator depending on K and L, but which we can hope to estimate. So if this error operator here in blue, EKL, was not there, then this would be exactly the CCR relations of bosonic particles. Okay, so that takes care of the interaction. What is more tricky is what to do with the kinetic energy. Because you see, kinetic energy already here is quadratic in these fermionic operators A star and A. I would like to have an expression that is quadratic in the bosonic operators B star K. So that would mean quartic in fermions. So that seems not so obvious how to do that. And in fact, we can only justify that in a rather weak sense. And to do that, we have to impose a discrete partition of unity on the surface of the Fermi ball. So we take the surface of the Fermi ball and we cut it in M regions. So these regions are labeled by an index alpha from 1 to M. And they are like in the picture here. So the precise shape doesn't matter so much, but basically you want to avoid that they elongate or degenerate into some weird shapes. They should roughly be rectangular. So this is an idea that I think goes back to Benedikter and Galavotti from 1990, and then was used very much also in the renormalization group community. For us, in second quantization, we have the representation that B star alpha K operator now is the same as the B star K operator from before, but localized to a region on the Fermi surface. Now, if we call the center of that region omega alpha, we can linearize the momenta around that point omega alpha, because in this sum enter only P's and H that are close to the omega alpha instead of distributed everywhere over the Fermi surface. And after this linearization, we find that the commutator relations simplify a lot. So the kinetic energy commuted with a pair creation operator B star alpha K becomes again a pair creation operator times some number, depending on K and alpha. So this is exactly the relation you have for the quantum mechanical harmonic oscillator. And that suggests that at least within commutators, we should be able to approximate the kinetic energy by a sum of harmonic oscillators, which means sum of all momenta K, sum of all patches alpha, the excitation energies, and the B star alpha K, the alpha K. It's a very weak approximation for the moment, valid only inside commutators. But it turns out it is the right approximation. So, okay. Maybe I shouldn't go too much into detail here, looking at the time. So if you go back a moment to this decomposition here, you find that I put in a normalization constant n alpha K. So that normalization constant I introduce by hand, and I want to choose it such that each of these B star alpha K omega operators creates a boson in a normalized state. Okay, so how should I compute this normalization constant? Well, you just demand that B star alpha K omega in Fock space norm is equal to 1. Then to achieve that, n alpha K squared should be exactly this sub that we had before already, but just with a delta P minus HK. So that's really just the number of all possible excitations you can make within a patch. So I sketched it over here in the graph. You have in the background the momentum lattice. Then this heavy black line here is the patch. Omega alpha points to the center of the patch. And then you have all possible ways of making a hole, like depicted here with an empty circle, and pushing it by a momentum K to a particle momentum depicted here by a black circle. When you have to count all these possible excitations, you find that their number is proportional to the surface area covered by a patch. That's the total surface of the ball, 4 pi n to the 2/3 divided by number of patches, times this geometric factor here that you obtain if you take the area of the patch and project it down to this region here depicted in black at the bottom. So I insist a little bit on this normalization constant since it plays quite an important role. Namely, it contains the same K scalar product omega alpha factor that you obtain, if I go back a moment, also from the linearization of the kinetic energy. So if you think of this from a perturbative point of view, that means in the interaction, you obtain these geometric normalization constants. From the kinetic energy, you obtain the same factor K dot omega alpha from the dispersion relation linearized. So if you think of a perturbative expansion as a power series expansion in interaction divided by kinetic energy, these factors cancel out exactly. And this plays actually a quite important role to get finite results. So if you go into the technical estimates, you see in many instances this cancellation of these factors, one of the geometric origin, one having origin in the dispersion relation, canceling out. So putting everything together now in the Hamiltonian, we have this B star alpha K, B alpha K part from the harmonic oscillator approximation for the kinetic energy. This U alpha squared here now represents this geometric factor. And I have the interaction, which is the same as before, B star B, B star B star plus BB, just decomposed according to this partition of unity over patches. Now this Hamiltonian looks exactly like a Bogolyubov Hamiltonian. It's quadratic in B star and B operators. And if I forget the error term in this approximate CCR relations, it is a quadratic bosonic operator. I know how to diagonalize that. I diagonalize it by Bogolyubov transformation, which is a unitary transformation on Fock space, which preserves the canonical commutation relations of the bosonic operators. And it has an explicit formula, namely this one given here, an exponential of something quadratic in B star operators. So there's a matrix of coefficients kk alpha beta run over the patches, k is sort of an overall parameter that we sum. And if you apply this transformation to the bosonic operators, you find this nice form indicated here. So B is being transformed into a cosine hyperbolic of the matrix K, again times B, plus a sinh hyperbolic of the B star of the same matrix K, acting on the B star operators. So you have a linear combination of B and B star operators such that the commutation relations are preserved. Of course, if the CCR relations for the bosonic particles are exact, and this is an identity for us, it is not an identity, it's only an approximation with error terms to be controlled. But okay, if we forget about the error terms, we can plug this expression inside in, transform the Hamiltonian with that. So T effective Hamiltonian T star, you compute it, you find that in good approximation, it's a system of decoupled harmonic oscillators, B star B, and you get the ground state energy of each of the harmonic oscillators, which sums up to exactly the RPA formula I showed in the beginning in the theorem. So the degree of freedom you have here is the choice of the matrix K, which you optimize such that the B star terms and the BB terms vanish, so that you are left only with these B star B ones. Okay, at this point you can read off the RPA energy to turn this into a proof. For the upper bound, you plug in a trial state, which the natural one for us is RT omega. For the lower bound, you first have to isolate a priori estimates on the kinetic energy of excitations, and then that permits you to transform the Hamiltonian while controlling error terms and again extracting the RPA energy. Okay, so maybe take home message of this a bit technical discussion is we define these pair operators B star that are composed of creation of a particle and a hole. We represent the hole interaction in terms of that. We represent the kinetic energy in terms of that. And then we can, by usual bosonic Bogoliubov theory and very good approximation, diagonalize the Hamiltonian. Okay, so at that point you have found the ground state energy. Now let me tell you a little bit results about the further physical properties of the system. So you see from this formula I gave on the previous slide, you don't get only the RPA energy, you can also potentially read off here the excitation energies of harmonic oscillators. They would correspond to excitation energies of the system. You just have to understand and diagonalize this matrix E here. Okay, so this matrix E is relatively complicated. I mean, it involves a couple of operator square roots, and we cannot compute it completely explicitly, but I can pick a finite value of M, so this matrix is finite dimensional without intending to let it go to infinity. So here I did this exercise actually for M equal to 20. I put the matrix in Mathematica, and you can diagonalize it numerically. So on the horizontal axis, I plot the momentum K of the particle-hole pairs, which in the matrix enters just as a parameter. On the vertical axis, I plot the eigenvalues of the matrix, so excitation energies for a given particle-hole pair momentum. In the non-interacting case, the plot is exactly the one here on the left. So you should think of this as the number of patches goes to infinity. It would approximate a momentum, a continuous spectrum below this upper line here. Now, if you switch on a short-range interaction in the system, the top eigenvalue starts to move a little bit, but a limited amount. So for this plot here, I made the plot with interaction potential V hat of K equal to e to the minus K squared, a Gaussian position in momentum space. What is interesting is the entire bulk of the spectrum can really not move. That has a reason, because you're looking at something like a second quantization of a rank 1 perturbation of a diagonal matrix, and you know that the perturbed eigenvalues cannot move more than the unperturbed ones. So the perturbed eigenvalues are locked between the positions of the unperturbed eigenvalues, except for the one at the very top. Now, if you go to a more singular interaction, like V hat of K is equal to 1 over K squared, the Coulomb interaction, this top eigenvalue actually starts to separate completely from the rest of the spectrum. So you have this big order 1 gap here, and the bulk that, as before, remains rather invariant. So this is actually very interesting, and this can actually also be measured in experiments. So what physicists do is they take a very thin foil of metal and they start shooting electrons through that foil, and they find that the absorption of energies of these electrons passing through the foil is exactly in multiples of this plasmon energy. Okay, so the first prediction of that is the one going back to Bowman-Pines in 53 that I mentioned early on. So Bowman-Pines use a very different method. So by systematic Bogoliubov theory, I wrote up this computation in 2020 under the assumption that the bosonization is exact. So no bosonizable terms, no CCR error terms. And then Christiansen, Heinzel, and Nam controlled the error terms of the CCR deviation, while not controlling, however, the non-bosonizable terms. So up to date, there is no complete proof of this picture of the spectrum. But yeah, so this we actually found pretty difficult to describe completely. We found a bit a way around to understand better the spectrum by looking at the dynamics. Namely, we were able to say, well, I should read this diagonalized Hamiltonian as the bosonic second quantization of a one-particle Hamiltonian HB. And then I can define one boson states that now live in a direct sum of CM spaces. I can define bosonic creation operators for a state, for a particle, for a pair state, for a pair of particles in state eta. And then if bosonization would be exact, these pair states should evolve in the one boson space by a Schrödinger equation with Hamiltonian being this matrix HB here, which is this direct sum of the EK matrices. Okay, in this picture, we were actually able to verify. So we were able to show that if I start with an initial state that has M bosonic pair excitations in it, on top of the Fermi ball, on top of the ground state of the bosonic problem. And so we have here the Fermi ball R, the Fermi ball created by the unitary transformation R. We have the unitary transformation T that brings us to the ground state of the bosonic Hamiltonian, and on top of that we put bosonic excitations. Then we evolve with the full many-body Hamiltonian, and we find that this is a very good approximation in L2 of the n-particle space norm, given by each of the bosons evolving by the bosonic one-particle Hamiltonian. That's a normal approximation of the n-particle system, and that's valid up to times, well, of order n to the 1/45. We can apply that in particular to eigenstates of the effective one boson Hamiltonian. If you plug in these approximate eigenstates, you find that they evolve under the many-body evolution, just like by a complex phase. Okay, up to times of order n to the 1/45. So for large particle number, we can go up to relatively long times where these effective excitations remain stable under the fermionic evolution, however. Okay, so the last thing I want to mention is the momentum distribution, what I also started with. So recently with Sasha Lil, my postdoc, we were able to compute the momentum distribution, at least of the trial state. It was actually already quite difficult. And we were able to show that, say, excluding some singular directions, the momentum distribution, so number of fermions with momentum k, is very close to the one of the step from 1 to 0 up to n to the minus 2/3 corrections, given by this big formula here. Okay, and so the picture you should have in mind here is that what we're computing is exactly the deviation from this perfect step here. So the real momentum distribution is going to deviate, is going to be a bit lower here, and it's going to be a bit larger outside the Fermi ball. And this is exactly the quantity that is here on the right-hand side of our formula. So I wrote less or equal because we have some direction where we put corridors between the patches that we have to exclude that don't contain any excitations for us. But if I'm looking at most possible k, then this inequality here is actually an equality. And that corresponds to the picture given down here in the corner. So in particular, we can conclude that the trial state in its momentum distribution has a jump of height indicated here as z. That is 1 minus c to the n to the minus 2/3 plus some small correction term. And that is in agreement with the results, for example, of Daniel and Voshko from the 60s. So at least for the trial state, we can confirm that the Fermi liquid picture holds in the mean field scaling limit. Of course, generalizing this to the true ground state would be very nice, but I believe also very difficult endeavor. Thanks.
Thank you very much for this nice talk. Are there questions?
What complicates the extension to the ground state? Your last comment.
Yes.
What complicates the picture?
Yeah, the difficulty is that making a single excitation that takes the occupation number of a fermion from 0 fermions to 1 fermion can cost you as little as order h bar squared energy. But the resolution that we get with the Bosonization approximation is order h bar. So we would need 1 order more of resolution of the energy to really say something about the momentum distribution of the ground state. So I believe that it's extremely hard to obtain this momentum distribution by going through the energy of the state. You have to do something working directly on the state, I believe, because the precision is, I think, way beyond what we can expect to prove for the energy.
Okay, any other questions or remarks?
Yes. On I think it was like 15 where you said that or explained how to diagonalize this Hamiltonian. So in the exact Bogoliubov case, you get a quite simple equation you can just solve if you do the step. Is it a little bit harder here, or do you have to
Our
use
approach is
we
pretend that everything was exactly bosonic, then we solve the equation, we obtain the correct k to use, and then we plug that in. And then we repeat the computation with all the error terms.
Okay.
The k is the same as in the perfectly bosonic case.
Okay.
Okay, any other questions?
Yes. I have several questions, but this is about this momentum distribution again. So you said that you see the indication of Fermi liquid nature for this the trial state for the optimal upper bound. But so if you look at this trial state, don't you see more direct or other characterization of Fermi liquid nature?
For me, this is my favorite characterization of Fermi liquid. I didn't look at any others, but I would be curious what you would suggest, and we could try to verify.
Of course, this should be the most direct, but yeah. So actually, have you shown us the formula for this optimal trial state in this talk, or
yes, so not completely explicitly. The trial state we should use is this RT omega, which is the combination of the transformation written up here and the particle hole transformation that just has the purpose of filling up the non-interacting Fermi ball.
Okay, thank you. So it's not something too complicated.
No, I think it's pretty nice and has a clear interpretation.
Okay, thank you.
Okay, any other questions? So maybe let me ask a question. When you talk to physicists, then typically when they want to improve over the Hartree-Fock or Thomas Fermi, when they start using things like density functional theory or Kohn-Sham equations, is it somehow behind, related to your approach, or is it completely orthogonal?
Yes, so the leading orders in the result, this one here, that one is the one you get from density functional theory in its simplest version. There's Thomas Fermi theory.
Yeah.
And actually, quantum chemists often, when they say they do Hartree-Fock, in reality, they do density functional theory with some, say, semi-empirical terms in the functional that are supposed to model the exchange term of Hartree-Fock theory.
Right.
And you can write similar sort of semi-empirical density functional terms that correspond to the RPA energy. So I talked actually to quantum chemists and they showed me how they compute RPA effects. Yeah, I think it's not really from first principles.
I see. Okay, maybe some other questions?
Yes, can I ask a more stupid
Yes.
question? So here, this bosonization is used as a mathematical technique to prove things, but should I understand that there is something really something physically going on to generate bosons, or you mean, is there?
Partly, yes. Like these plasmon excitations that you observe in experiment, they behave really like bosons. But that's the rest of the spectrum is more to think of as fermionic. So you see here you have a big gap between the plasmon and the rest of the spectrum, which makes it fairly stable. Up here, the gap is very small. Actually, if you try to measure the plasmon energy up here at large momenta, you see that it starts to dissolve into the bulk of the spectrum, which you see the bulk of the spectrum is the same as in the non-interacting case. So that is identical to the fermionic description.
But does this plasmon behavior related to the bosons that you introduced by using this bosonization, or is it just accidental?
I mean, if here in these weighted bosonic operators, I plug in the wave function that corresponds to a plasmon, this gives me here an effective eigenstate.
Okay.
That evolves really as a bosonic particle.
Oh, interesting. Thank you.
Of course, in our result here, there's no distinction between the different kind of bosons. The plasmon, which should be much more stable than the rest. So it would be an interesting question to see if for the plasmon one can, for example, improve the times of stability here. We don't know.
Okay, are there more questions? Does not seem to be the case, so let's maybe thank the speaker for this nice talk and close the official part of the meeting. Hopefully we can still chat and ask more informal questions after. So let me
Thank you very much for the attention.